Every opinion poll, medical trial and scientific paper has one problem. You can never measure everyone. So, how do statisticians make reliable conclusions from just a sample? In this video, we'll be going over confidence intervals and how they are used in real life to give a range of plausible values of the real value. We use confidence intervals because we are taking, for example, a survey of people's heights. We use 100 people and can take the average of those people. But we want this to represent the average height of the entire population. However, the average height of the group is not necessarily going to be the average height of the entire population. So we give ourselves a range and a percentage linked to that range, which will be our quote-unquote confidence. So if on our survey the average male was, say, 177 centimetres tall, we would give a confidence interval, for example 175.5 to 178.5 centimetres tall, as we would be that percentage confident that the actual value fits somewhere inside this interval. So how do we figure out this interval? Now, we work this out from a normal distribution. We will take the variance, the mean, and the number of observations. Depending on the percentage confidence we have, maybe 95%, we associate a z value to it, which you can look up the exact z value for. So z 0.95 is going to be split in half. For a 95% confidence interval, 95% sits in the middle of the normal distribution and then leaving 5% outside. Since the normal distribution is symmetric, that's 2.5% on either side. So when we look up the z-score corresponding, we use 97.5%, so z 0.975, which from looking it up is 1.96. So we have a variance, which we'll know before the z-score, the mean that we got from our data, and the number of people. If we place this into the formula, mean plus or minus z times square root of variance divided by the square root of observations. Let's show this with the heights example. Say we know that the variance is 49. The mean from the experiment will be 177 centimetres, and we used 100 people in our experiment. Now we're going to use a 99% confidence interval. So first, to get the value of z, we once again need to split the interval to either side. So we are now looking at z 0.995 for this interval. From looking it up, we can identify that the value is 2.5758. Now place that into our values. Mean 177 plus or minus z 2.5758 times square root variance 7 divided by square root n 10. This evaluates to approximately an interval 175.2 centimetres to 178.8 centimetres. This physically means if we repeated this entire experiment thousands of times, each experiment we would produce a different confidence interval. Around 99% of those confidence intervals would contain the true population mean. A quick note here, if we don't know the variance already, which is probably most of the time, and have to work with it ourselves, then I'm not going to get too much into it, but replace the z value with what is called a t value, which will also take into account the number of observations n in the experiment. T values with infinite observations are z values. This is why the central limit theorem is so important, as now by taking any distribution, we can write the averages into a normal distribution, and as we said last video, and now we will be able to use the confidence intervals as shown above. Confidence intervals don't tell us the exact answer, they tell us how uncertain our estimate is. The larger our sample, the smaller amount of uncertainty. If you found this video helpful, please like the video and subscribe to support the channel, and I hope to see you in the next video.